So, good morning students. We were doing in the last class linear system of equations. Okay? There we discussed why we need to study again the linear system of equations. Then we did the Gauss elimination method. There we discussed about the pivoting technique, the first one, that is partial pivoting, and we had seen that about the pivot equation, etc., and how you interchange the rows depending upon the pivots, whether it is 0 or not, depending or less than the below in this column. If suppose this 6 is smaller than these elements in this column, then we should switch according to the maximum absolute value of these elements. So, like that in each iteration these to be done, and that is called the partial pivoting. Now, we will do the next pivoting technique, that is scaled pivoting. So, scaled pivoting so this pivoting technique I will discuss in terms of an example. So, let us take one example such as 2x1 minus x2 plus x3 is equal to 1 or minus 1, 3x1 plus 3x2 plus 9x3 is equal to 0, 3x1 plus 3x2 plus 5x3 is equal to 4. I have these three equations, three unknowns. Now, as per the scaled pivoting, first of all I should write the augmented matrix A tilde that we have discussed in the last class. The coefficient matrix, this 2 minus 1 1, 3 3 9, 3 3 5. Then we augment it by the right hand side vector minus 1 0 4. This is your augmented matrix to start with the Gauss elimination process. So, here as per scaled pivoting, the technique is I have to first take all the pivot elements. So, I will make one table, elements in pivot position, maximum value in that row, maximum absolute value in that row, and scaled element in pivot position. So, these are the three things I need for this system. Okay? So, elements in pivot position, maximum absolute value in that row, scaled element in pivot position. So, I have three rows to this, this and this. So, in the pivot position, these are the elements in the pivot position. Any of them may be pivot depending upon the procedure. Okay? So, I will write first 2, 3, 3. These are the elements in pivot position. Now, I will check maximum absolute value in that row. So, in this row, maximum absolute value is itself 2. Fine? So, I will place 2 here. In the second row, maximum absolute value for this is this 9. Fine? So, this will write 9 here. Next, for this row, last row, maximum absolute value is 5. So, this is your 5. Understood? So, first is elements in the pivot position, then the maximum absolute value in that row. Now, I will scale this element in pivot position, means I will divide this 2 by 2 as 1, 3 by 9, 1 by 3 and 3 by 5, that means 0.6. This way we first scale, then I will check about the absolute value or value of this, the maximum one. So here by chance maximum is 1, fine, 1 by 3 is your 0.33, so the maximum is 1. So the scaled pivot element is 1, which comes from the first row, so we will not interchange. Suppose I got for some other elements, this as the maximum, that means I have to switch the last row to the first, understood? If I get the maximum here, so I have to then interchange the second row with the first, understood? So after doing that, whatever Gauss elimination method is there, you will make it 0. Only this scale pivoting is to know which is the first pivot element. So in this case, this will remain the same because I got as maximum value here for the first row. Okay? So you do this. I am not going to complete this. You can change this to 0, then you can change this to 0. Okay, you can see that after doing this 0, you have to again apply this for the second operation. The same scale pivoting means that time you will have this and this, although this will be changed after the operations. So this and this you will write now, 2 elements will be there, this and see what are the maximum. Then you divide like this, and you will see in the next operation you have to interchange these 2 rows. Okay? So I will not do incomplete, I will write the last answer as x1 as 1, x2 as 2, x3 as 1. So this is the answer for this problem, but again you can see that because this is a very small system with good coefficients, good means we don't have very small numbers here, small or very large or small depending, so it is a well conditioned system, so you will get the same result if whether you apply the pivot technique or not. Okay? So in this way we have discussed 2 pivoting techniques. One is your partial pivoting and other one is scale pivoting. There are other procedures also about the pivoting. We will not do that, but we will now switch to other methods for solving the linear system of equations. Okay, fine. So after this Gauss elimination method, we will see another method namely of LU factorization methods. In these methods, you have 3 methods actually. So we will see one by one. So this is your LU factorization methods. So this LU means L stands for lower triangular matrix and U for upper triangular matrix. So L for lower triangular matrix and U for upper. The method's name is LU factorization methods. So what we will do, given the system Ax is equal to B, so remember our system is Ax is equal to B. A means your coefficient matrix, X is your unknown vector, B is your right hand side vector. So A may be order n by n, so it will be n by 1, this is n by 1. So our aim here will be to factorize this A to L into U. Okay? So to factorize this we have 3 methods that we will do. By 3 methods, that means one will be this A will be converted or factorized to lower triangular into upper triangular matrix. So let us understand this by a 3 by 3 matrix. So that means I have A 3 by 3, X 3 by 1 and B 3 by 1. Okay? So let me take an arbitrary matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. This is your given 3 by 3 matrix. Remember, all the elements of these are known because I have the system given as Ax is equal to B. B also we know. Okay? And I don't know only this x. I have to find the x. That means all the elements, how many elements are there? 9 elements, because 3 by 3, so 9 elements. Now I told I have to factorize this to L into U, that means lower triangular into upper triangular matrix. So let us write this multiplication of two matrices L and U. So lower triangular matrix means like this. Fine. This is your lower triangular matrix where we don't know these Lij's till now. We don't know these Lij's, but we know the elements of A. Fine. And let us write the upper triangular matrix, that means U11, U12, U13, 0, U22, U23, 0, 0, U33. This is your upper triangular matrix where I don't know Uij's. Fine. I have to find these Lij's and Uij's using these elements. Fine. What I can do, I can multiply these two matrices. So this is 3 by 3, this is 3 by 3. You will get a 3 by 3 matrix. Fine. Now if you multiply, now you see this side is 9 elements. Those are known. Now how many elements unknown are here? This L matrix is having how many elements as unknown? 6. 1, 2, 3, 4, 5, 6. 6. Here again 6. So 6 plus 6 is 12. So 12 elements are unknown. Here 9 elements known. So now after multiplication, this side, right hand side, you will get a matrix. Okay. Now each element by element I will equate. How many equations you will get? How many equations? 9 equations, because 9 elements are there. And how many unknowns? 12. Can you solve that? No. Fine. So that is why, see, that means here 12, that means 3 elements are extra which are unknown. Okay, if I know those 3 elements, any 3 elements, then I can solve and find these Lij's and Uij's. Understood? So now for reducing this to 9 unknown elements, we have 3 methods one by one. Okay, first one is called Doolittle method. Second is Kraut method. Kraut method. Third is Cholesky. So that means first I have to factorize this A coefficient matrix to L into U, and you are seeing that I have 3 extra elements. Okay. So what he did, this Doolittle, he substituted this Lii as 1 arbitrarily, Lii as 1. So that means L11, L22, L33 is 1. For this example, I is 1, 2, 3. Fine. So now it will be reduced to 9 elements, because I have supposed these are all 1. So I have 9 elements this side, 9 elements this side, 9 equations, 9 unknowns, so I can find those. Fine. So he did this. So after this, now Kraut thought, why I will take Lii, I can take also Uii. That is another method. So he put Uii as 1 for I is equal to 1, 2, 3. So this Uii as 1. So again it is converted to 9 unknowns. So that is the second method. Third method, Cholesky, what he did then, why I will put 1, 1? I will take these are same. LII as UII. Again it is reduced to 9. Okay? So then we took LII as UII, I is 1, 2, 3. Fine? So again it is 9 elements, although here some condition is there that we will discuss afterwards. So I have 3 methods depending upon these, whether LII as 1 or UII as 1 or LII equal to UII. Now let us see what will happen if so now by these 3 methods you can, that means factorize this coefficient matrix A to L into U. Okay? That we will see by example also. Okay? Now that means I have factorized A to L into U. Remember our system is Ax is equal to B. Fine? So if Ax equal to B, this A equal to Lu I can put for A as Lu. This A I can put as Lu. Fine? I have substituted this A because I have factorized 2 L into U. I am substituting for A as L into U. Now I will assume Ux is equal to Z. And remember, when I have factorized, that means I know now Lij's and Uij's. So Ux is equal to Z. Fine? Now substitute this Ux equal to Z here. So what you will get? Lz is equal to B. Now you see these 2 equations. See, we will do first this, then this. See, Lz is equal to B, where L is known after factorization, B is known because it is given, B is known, it is given. So Lz is equal to B, Z you can find, Z vector you can find, and that too because I have lower triangular matrix. So by directly forward substitution, you don't have to do all Gauss elimination. Just forward substitution you will get Z. So if it is 3 by 3, you will have Z1, Z2, Z3. Fine? Lz is equal to B. So if you know Z, now I will use equation 1. In equation 1 you see Ux is equal to Z. U you know from the factorization. So U you know, Z from this equation 2 you know, substitute Z here, you can find X. Understood? You can find X. U is known and Z is from here, equation 2. So I can find X. So here, so again you can see this Ux equal to Z is also directly back substitution because you have this Ux, U is this. These elements are 0. So directly by back substitution you can find x1, x2, x3. Fine? So here main difficulty is what? Main difficulty is to factorize A to L into U because you will have 9 equations. Although those are simple equations, you will just multiply, you will get suppose L11 into U11, then this into this, like that. Different elements you will get in terms of Lij's and Uij's. You have to equate each element with these elements because you know Aij's. Okay? So that is the main actually difficulty to factorize A to L into U, and then it is very easy. First Lz is B, L is known from that factorization, B is known from given system Ax equal to B, so you can find Z directly without doing any means only the forward substitution. Now Z you substitute here, U you know, Ux equal to Z, X you can find directly by back substitution. Okay? So those Gaussian elimination operations, if it is large system, is not required here, but difficulty is there about this factorization because if it is a large matrix, more equations will come, but I can write in a systematic pattern, you can write the program and you can have these L into U. Because I already told that these all methods are with respect to your computer. Actually by hand we are doing to have the practice. Okay? Fine? Now let us take one example and see what is happening actually. Okay, solve by Doolittle method. given system is 2x1 minus x2 plus x3 is equal to minus 1, 3x1 plus 3x2 plus 9x3 is equal to 0, 3x1 plus 3x2 plus 5x3 is equal to 4. Okay, so I have 3 by 3 system. Okay, so I can write A and B as that you know already. A as 2 minus 1 1, 3 3 9, 3 3 5, and your B is minus 1 0 4. So first task is to factorize A to L into U. Okay, fine. So I have this A, that means I have to write A as L into U. So I have this A as 2 minus 1 1, 3 3 9, 3 3 5. This I have to write multiplication of two matrices, namely lower and upper triangular matrices. And remember, I am using Doolittle method, so your diagonal elements of lower triangular matrix to be unity. Okay, fine. So what I can write? 1 0 0, L 2 1 1 0, L 3 1, L 3 2 1. Is it fine? You see that L 1 1, L 2 2 and L 3 3 I have substituted as 1. And that upper triangular matrix is U11, U12, U13, 0, U22, U23, 0, 0, U33. Okay? So I have here 9 elements known, here 9 elements unknown. I can multiply these two matrices and then term by term you equate. So you will get all Uij's and Lij's. So if I multiply this, what you will get? So you can see very well this into this. So U11 is directly, U11 is 2. Then this into this if I do, so U12 is minus 1. And this into this, so U13 is 1. So these three were very simple, so I did this. The other one you will do. So next will be what? This into this. So you will get here L21 into U11, where you know U11. So like that, using these three and other Uij's and Lij's, you can just find from this matrix. Okay? So that you will do. After that, what I will get, I am just writing directly the L and U matrices. 2 minus 1 1, 3 3 9, 3 3 5, and L matrix is 1 0 0, 1.5 1 0, 1.5 1 1, and U matrix is 2 minus 1 1, 0 4.5 7.5, 0 0 minus 4. Fine. So after solving this system like this element wise, so we will get this as L and U, and you know what is B. So okay, first you will go with this. So X is equal to B, I can substitute for A as LU, X is equal to B, and we suppose that Ux is equal to Z, then Lz is equal to B. So Lz is equal to B. That means I have Lz is equal to B, so I will have Lz 1 0 0, 1.5 1 0, 1.5 1 1. into Z. Remember, Z components will be depending upon the order of the matrix. Okay, here 3 by 3, so it will be Z1, Z2, Z3. Fine. If I give 4 by 4 or 5 by 5, it will not come Z1, Z2, Z3, Z4, Z5. Fine. Is equal to B. B is your minus 1, 0, 4. Fine. So minus 1. So now you can see directly Z1 is minus 1. Z2 is 1.5. Z3 is 4. So you can see directly by multiplying 1.5 Z1 plus Z2 is equal to 0. You have Z1 minus 1, substitute that, you will get Z2 as 1.5. Similarly, last equation 1.5 Z1 plus Z2 plus Z3. Z2 and Z1 you know, so Z3 is 4. So you know now the Z. So next is Ux is equal to Z. U is your that matrix, already we have found 2, minus 1, 1, 0, 4.5, 7.5, 0, 0, minus 4. And X is your X1, X2, X3. And Z we have found as minus 1, 1.5, 4. So this is your Ux is equal to Z. So here I know U, I know Z, so I can find directly by back substitution. So X1 is 4. Similarly, X2 and X3, sorry, this is X1 or X3? X3, because back substitution. I am going from here. Minus 1, sorry, yes. 4 by minus 4. So it is minus 1. X2 is 2 and X3 is, sorry, X1 is 1. Is it okay? So I have the X as 1, 2, minus 1. So this is the procedure as per the Doolittle method for solving linear system of equations, where you have seen the difficulty only is to factorize from A to L into U, because you have 9 equations, 9 unknowns. You have to solve this. After that, it is only Lz as B and Ux as Z. Okay, fine. Similarly, I can have the other method, that is Kraut's method. So let us take the example for Kraut's method. So Kraut's method, I have the example like this. 3x1 plus x2 is equal to minus 1, 2x1 plus 4x2 plus x3 is equal to 7, 2x2 plus 5x3 is equal to 9. Fine. So in the Kraut's method, I have A is equal to LU, where your UII as unity, only this is the change. Fine. So A is your here what? 3, 1, 0, 2, 4, 1, 0, 2, 5. This is your A. L will be what? L1, 1, 0, 0, L2, 1, L2, 2, 0, L3, 1, L3, 2, L3, 3, and into U. U I have how? 1, 1, 1, U1, 2, U1, 3, 0, 1, then U2, 3, and 0, 0, 1. So you can see again 6 elements, only the change is here, this UII as unity. So again you can multiply and equate with each elements of this A matrix, find L and U, okay, then use the same Lz is equal to B. See, here also same thing will happen. I have Ax is equal to B, I have factorized A to L into U, so Lux is B, only the procedure here is changed for U matrix for the Krauts method, but the other procedure are same. So Ux is Z and Lz as B. So these two equations will give you solution. Okay, so next class we will write all these L and U and we will write the solution. Okay. So we have one method left for LU decomposition, that is Cholesky method, that we will do in the next class. There we require some conditions also to apply Cholesky method, that we will discuss in the next class. Okay, thank you very much.